Well, we're going to try a little experiment here. The section in my book that this really deals with is about geometric sequences, but I can't seem to keep myself from bridging out a little bit here and touching on other kinds of sequences. So, for the first time, one of these ShowMes is going to expand into what I think is absolutely necessary to understand and put a narrow topic in its place. So I'm going to talk about sequences. The first thing we'll talk about is arithmetic sequences, then geometric, then polytopic, which actually very familiar. In fact, in a way, you'll be surprised that polytopic sequences aren't called geometric. Finally, we'll just touch briefly on Fibonacci's sequence and its connection to Pascal's triangle, just to give you a flavor of how and where mathematicians find and generate sequences. As always, I'd love to discuss any of these topics, including any particular problems that are giving you trouble, at my blog at MikePoliquin.com. So as promised, let's start with arithmetic sequences. Here before you, you see an example of an arithmetic sequence. An arithmetic sequence is built on repeated additions of the same number. In this case, we start with a first term of 2. We'll give that term a name A. And then in generating the other terms, we repeatedly add 3. 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11, and 11 plus 14 is 3, and the ellipses tell you that that pattern is going to continue indefinitely. This number 3 that we are adding in each case, we call the common difference. And we give it a name. We call it D. Now this is a sequence, and that means that the numbers in it are paired up with the ordinal versions of natural numbers. 2, for instance, is paired with 1, because it's the first number. In the same way, 5 is paired with 2. Now I'm writing ordered pairs for a reason. These numbers, these ordered pairs that I'm writing, actually form a straight line when plotted on the coordinate plane. Now the space in between them is not filled. These are simply dots on the coordinate plane, but all of these dots are on the same line. So there is a very strong connection between the idea of an arithmetic sequence and the idea of a straight line, which is why in the course that I'm teaching in Algebra 1 right now, we talked about arithmetic sequences as a lead-in, as a beginning process for our 2 chapters that we spent on lines. That's the basic terminology for arithmetic sequences. That's the vocabulary of it. Finally, you need to know there's a formula for every single arithmetic sequence. It can be applied and fitted to any such sequence. The formula is this. We look at a sequence as a function. It's a function of a natural number n. The natural numbers start at 1 and go up by 1 forever. So the first number that goes in for n in this function will be 1. The domain is the natural numbers. This function consists of a sum. We add the very first term, which we called a. So in this case of the function up here, it would be 2. We add to that repeated additions of the common difference. Well, repeated addition, as we learned in elementary school, is multiplication. What are we multiplying by the common difference? Well, for the very first term, we don't want to add anything to it at all. We want to add 0. But for the next term, we want to add 1 instance of the common difference. To get the third term, we want to add 2 instances of it. 2 plus 2 times 3 is 8. But 8 is the third term. How do we pair 8 with only 2 additions of 3? The answer is that we use a factor not equal to the natural number that we're talking about, because 8, after all, is paired with 3. We use the number just below 3, which would be 2. How do we make that happen for every term in the sequence? We don't use n, we use n minus 1. And that is being multiplied, of course, by the common difference. So to get the 25th term, I don't have to count all the way out to the 25th term of the sequence. All I have to do is put 25 in for n. So 25 minus 1 is 24. The common difference, of course, is still 3. The first term is 2. So the 25th term of this sequence is 74. But I don't have to count out all the terms in between 14 and 74 to figure that out. The formula is very handy that way. It's also very handy because formulas like this are the sort of thing that you want to use in spreadsheet programs and other tools. That makes the mathematics that we all generate as mathematicians accessible to non-mathematicians, people that want to use math only for very narrow, specific purposes. And arithmetic sequences could be such a purpose. Anyway, that's the whole overview of arithmetic sequences. And there are many parallels between that and geometric sequences, which is where we're headed next. So, as before, I've given you an example here of a geometric sequence. This geometric sequence, like the one before it, starts at 2. And in the same way, we will give the first term the name A. So for this sequence, A is 2. But in geometric sequences, we're not adding to get the new terms, we're multiplying. To get to 6, we multiply by 3. And then to 18, we multiply 6 by 3. And to get each successive term, we multiply once more by 3. And again, the ellipses state that that goes on indefinitely. This 3 this time is not a difference because we can't subtract a new number, an old number from a new number to discover the difference and get 3. In fact, the difference between each of these numbers changes. 6 minus 2 is 4, 18 minus 6 is 12, 54 minus 18 is 36. One interesting fact about geometric sequences is that the differences between successive terms triple when 3 is the common ratio. That gives it away. We don't call this a common difference, we call it the common ratio. We call it that again because we can discover it using division, which is the operation we usually use to link ratios to mathematics. 162 divided by 54 is 3, and so on. In every case, there's a factor of 3 between successive terms. As with arithmetic sequences, we can structure ordered pairs. A sequence implies that there's a first, second, third, fourth term. Well, those ordinal numbers, first, second, third, and fourth, can be translated into cardinal numbers 1, 2, 3, 4, and 5, and paired with the numbers in the sequence, so that we have a domain full of natural numbers and a range of numbers that comes from the sequence. And they're paired just so. One interesting fact about this sequence is it's not going to make a nice, neat, straight line. These dots are going to seem to define a curve. And in fact, that's what it will seem to be when we do the graph. But remember, this is a sequence. There are no numbers to be graphed in between 1, 2, and 2, 6. Okay. So the connection is a parallel. The connection is analogous. It's not literal because this is not a function of the same type. The domain of this function is going to be the natural numbers. There are going to be holes all over this function. But nevertheless, it is a function, and that means we can write a function rule for it. We define that the same way that we did for arithmetic sequences, except, of course, the operation is not addition, it's multiplication. So we want our first term, of course, to be our first term. But we know that to get all the successive terms, we're going to multiply by our common ratio. So there has to be a factor involving our common ratio. Again, though, we don't want 2 to get multiplied by 3. That would make our first term 6. How then do we fix that? Well, first of all, note that to go from 2 to 6, you take 2 times 3. To go from 2 to 18, you take 2 times 9. 9 is 3 squared. And then to go from 2 to 54, you take 2 times 27. 27 is 3 cubed. So to get our fourth term, we had to multiply by our common ratio to the third power. To get our third term, we had to multiply by our common ratio to the second power. So it appears that we should use an exponent, and the exponent should be 1 less than the ordinal number that represents the term we're talking about. What does that mean in terms of straight algebra? Well, our exponent should be n minus 1. That way, when we start with 1 for n, we use 1 in the formula, we get 1 minus 1, which is 0. R to the 0 will be 1, and our first term will be a, which is what we promised ourselves we were going to do. So this formula applies then to all geometric sequences. Every single one of them can be fitted and laid out this way. Before I go on to polytopic sequences, I just want to point out some analogies between these two kinds of sequences. First of all, their formulas have similar structures. The first terms are in the same positions and are related to terms involving common difference or common ratio according to operations that fit the type of sequence. The common difference, of course, has a similar role in the arithmetic sequence as the common ratio in the geometric sequence. Both are repeated using the operation in question. Clearly, addition is to arithmetic sequences as multiplication is to geometric sequences. And clearly, multiplication is to arithmetic sequences, in the case of this addition term, as exponentiation is for geometric sequences. That makes sense. Multiplication is repeated addition, while exponents represent repeated multiplications. So there's some important parallels between these two. In the case of the course that I teach, the arithmetic sequences launched us into our investigation of linear equations. For geometric sequences, they're going to launch us into our investigation of polynomials, exponential expressions, and eventually a general solution of the quadratic equation. All of that seems like gobbledygook now to my students, but in just a couple of months it's all going to make sense. Here I want to present just 3 sequences of a type that we call polytopic. Polytopic sequences are everywhere. They are laced into all kinds of different geometric and physical concepts. And they have important implications, especially when we consider some of the multidimensional things people are trying to do in physics these days. Polytopic numbers begin with very simple, probably very familiar sequences. For instance, triangular numbers are based on the idea that we can build shapes out of dots, and the number of dots makes a sequence of numbers. For instance, triangular numbers begin with the assumption that a dot can be triangular, and so 1 is a triangular number. So 1 is defined to be the first. To make a triangle of dots, we can add a second row of dots that is simply 1 larger than the row above it, and then we have a new triangular number represented by the dots. In this case, there are 3 dots. Then if we add another row with 3 more dots, we have 6. If we add another row with 4 more dots, we have 10, and so on. Triangular numbers, you can formulate them fairly easily. The point is that each time you move up to the next number, it increases by a difference that is 1 larger than the prior. So to go from the first to the second, we went up by 2. To go from the second to the third, we go up by 3. And to go from the third to the fourth, we go up by 4. And that process continues. 15, for instance, the familiar configuration of billiard balls for pocket billiards, if you're used to playing pool. And it continues. 21, and then 28, and so on. Those are triangular numbers. They are defined by a matrix of dots that forms a geometric figure. And polytopic numbers work that way until we get outside the third dimension, outside 3-dimensional situations. And we're not going to go there today, but it is fascinating to go there. Square numbers work the same way. You have 1 dot. We assume that that could be a square, and so we have 1 as our first square number. Then to make a square out of more than 1 dot, one has to have at least 4. So 4 is the next square number. Then you have to have 9. And it turns out what you have to have is a number that represents the same number of both rows and columns. And so the next number after that would be 16. And then 25 and 36, and all the familiar numbers. And the way to get square numbers, there are 2 ways to do it. You could go up by increasing odd numbers, go up by 3, and then up by 5, and then up by 7, and then up by 9, and up by 11. Or we could simply take the sequence of natural numbers and square each item. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. And in fact, that's why we don't say to the second power in English. We say squared, because that's the sort of language that was used originally by the Greeks. After all, they weren't doing algebra at first. All of their numerical achievements were based on geometry, and they did some prodigious things with it. Finally, cubic numbers, just to round out the most familiar numbers. 1 can be a cubic number. Then to make a cube after 1, one requires 4 dots in front to make the front face of a cube, and then 4 more dots in back. And so while there are any number of edges and faces involved, in fact there are 12 edges and 6 faces in a cube, the point of the cubic number here is that there are 8 vertices. The next cube you can make actually involves stringing together 27 of these, and then discounting the dots that they have in common, and it's 27, and then 64, and then 125. Note that I was easily discouraged from drawing the cubic numbers. They become very complicated very quickly, and it was easy to discourage me because I already have a formula for them. Simply take successive natural numbers and multiply them by themselves twice. 1 times 1 times 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, and so on. Once you have a formula, constructing the whole sequence doesn't make a lot of sense. Much as we don't want to do that with arithmetic and geometric sequences, we want to create formulas for terms out into the far unforeseeable distance, and then allow computers and our technology to help us generate the numbers we actually need from each sequence. Anyway, those are polytopic numbers. They get a lot more fascinating as you push into higher dimensions and more complicated objects, and they have some surprising applications. Finally, one of the most fascinating and for me enjoyable ideas about sequences. The Fibonacci sequence is a sequence in which the 2 previous numbers are added together to make a new number. That makes it what we call a recursive sequence. It depends on the results of previous calculations. The only stipulation with Fibonacci is that we start with 1, and 1 is our first 2 numbers. To make the next number then, 1 plus 1 is 2. To make the next number, 1 plus 2 is 3. To make the next number, 2 plus 3 is 5, and then 8, and then 13, 21, 34, 55, 89, and 144. And I went that far because I've always thought it was fascinating that the 12th number in Fibonacci's sequence is equal to 12 squared, 144. It's a little intersection between the sequence of square numbers, which is a sequence that's always fascinated me and has been very useful, and the Fibonacci numbers. Anyway, Pascal's triangle is here on the screen for an important reason. The Fibonacci numbers are hidden inside it. If we work along diagonals parallel to this line that I just drew, we can discover by adding up all the numbers that we intersect all of the Fibonacci numbers. This line goes through 1. This line goes through 1. The next line, however, goes through 1 and 1, which are 2. The next line goes through 2 and 1, which are 3. And then 5. And then 8. And then 13. And then 21. I think it's just fascinating that those numbers are hidden there. But you would be amazed to see what else is hidden in Pascal's triangle. If we work across the rows, we discover all the powers of 2, or all the place values in binary. For instance, here's 1, 2 to the 0. Here's 2, 2 to the first. Here's 4, which is 2 squared. Here's 8, which is 2 cubed, and so on. Every single row adds up to a new power of 2. I think that's fascinating. Look at other diagonals along Pascal's triangle, and you can spot some other old friends. Obviously, the sequences of 1s down the sides are not terribly interesting, but drop down one level, and we have the natural numbers. Twice. Drop down another level, and we have the triangular numbers. All of them right there, neatly organized for us to find. So a lot of little patterns. I'm sure that there are others that I've missed, haven't mentioned here. But what I wanted to point out most about Fibonacci and Pascal's Fibonacci sequence and Pascal's triangle is that there's a lot of mathematics to be done just for the sake of math. It doesn't always have to be about applications. Now, it does when it comes to your state assessments. If nothing else, your math needs to apply to your assessments so your high-stakes tests can go well and your teachers can keep their jobs. But getting beyond that, mathematics is a fascinating area of endeavor just to explore in its own right. It leads into all kinds of deeper questions, philosophical, scientific, sometimes even theological, depending on what you're into. But it's just fascinating, and I want to invite you to dive into that. Places where you'll find that kind of work, two great places to start are anything about basic number theory, and of course, you want to find some real crazy folks who have some wild ideas about math, get into the history of math. Mathematicians are not boring people, not the great ones. They're fascinating. Some people have become renowned as mathematicians without even being mathematicians. Pythagoras was no mathematician. He was a cult leader. Some would say a crazy one. He was kicked out of at least 2 cities during his lifetime. Why do we honor Pythagoras? Well, when he was lost to them, his followers split into 2 groups. One group continued with a very ascetic lifestyle, vegetarianism, and all kinds of interesting beliefs about reincarnation. The other group focused on mathematics and an exploration of proportion. And those are the folks that helped foster an amazing explosion in knowledge in the Greek civilization, helping to form one of the main pillars of Western civilization. Anyway, I just want to invite you into that. I don't think we do enough of that as math teachers, but I think it's fascinating. And if you do too, let me know at my blog. We can look together for some resources. We can have a dialogue. I don't know if you can have that dialogue with every math teacher you've got. There's so much business that has to be done in class. But if you want to have it with me, my blog is there, and I am too.